civilization has always been shaped by how we move. From the wheel to the jet engine, every leap in transportation rewrote society itself. Now, for the first time in history, physics, artificial intelligence, and advanced materials are converging to lift our cities off the ground, turning science fiction into an engineering problem waiting to be solved. For more than a century, flight belonged to a privileged few pilots trained to master complex machines, backed by massive runways and global infrastructure. Yet the laws of physics never declared that the sky must remain exclusive. In fact, the same equations that describe the lift of an airplane wing, the thrust of a rocket, and the stability of a satellite also quietly permit a future in which personal flight becomes routine. At its heart, flight is a negotiation with gravity, a balancing act between downward pull and upward force, and once you understand that gravity is not an enemy but a predictable constant, the problem becomes engineering rather than magic. Advances in aerodynamics, lightweight composites, and computational modeling now allow us to design vehicles that manipulate air with extraordinary precision, squeezing lift out of small surfaces and stabilizing motion with millisecond correction. What once required intuition and bravery can now be managed by algorithms that calculate thousands of variables every second, turning turbulence into data and chaos into control. The real revolution begins when propulsion itself changes character. Traditional aircraft rely on forward motion to generate lift, demanding long runways and open skies. But vertical flight rewrites the rules by separating lift from speed. Rotors, ducted fans, and distributed electric propulsion systems can generate lift directly, allowing vehicles to rise straight upward like elevators in the sky. Physics makes no objection to this. It simply demands energy, balance, and stability. Electric motors are particularly well suited to this task because they deliver instant torque, precise control, and high reliability with far fewer moving parts than combustion engines. When dozens of small motors replace one large engine, redundancy becomes a feature rather than a flaw. If one motor fails, others compensate, guided by control systems that respond faster than any human pilot could. The sky, once perceived as dangerous and unpredictable, begins to resemble a carefully managed fluid navigated through mathematics rather than instinct. As flight becomes more compact and controllable, the implications extend far beyond the vehicle itself. The true obstacle to flying cars was never the sky, it was the city. Horizontal cities evolved around roads, intersections, and traffic lights, flattening human movement into two dimensions. Vertical takeoff and landing introduces a third dimension into daily life, forcing urban planners to rethink space itself. Physics, again, plays a central role because vertical motion demands careful management of thrust, noise, airflow, and energy dissipation. Buildings are no longer passive structures but active participants in transportation networks. Rooftops become ports, balconies become docking platforms, and skyscrapers transform into nodes in a three-dimensional grid. The city ceases to be a flat map and becomes a volume layered with corridors of motion stacked one above another. This shift fundamentally alters how distance is perceived. In a vertical city, proximity is no longer measured only in meters but in seconds. A destination directly above or below may be closer than one a few kilometers away on congested streets. Physics teaches us that the shortest path between 2 points is a straight line, and vertical mobility finally allows cities to approach that ideal. The result is a dramatic reduction in wasted energy and time as vehicles move efficiently through open air rather than crawling across friction-filled surfaces. Congestion, a byproduct of limited dimensions, begins to dissolve when movement expands into three-dimensional space. Traffic jams are not an inevitability of civilization. They are a symptom of constrained geometry. Energy, of course, remains the critical currency of flight. Gravity demands payment in joules, and no technology can evade that bill. But the efficiency of energy use has improved so dramatically that the cost is no longer prohibitive. Advances in battery chemistry, power electronics, and regenerative systems mean that energy lost during descent can be partially recovered, much like elevators that feed electricity back into the grid. Physics rewards efficiency, and modern designs exploit this by optimizing every gram of mass and every watt of power. Lightweight materials inspired by aerospace engineering reduce structural load, while smart systems distribute power only where and when it is needed. The result is not just flight, but sustainable flight, integrated into the broader energy ecosystem of the city. Vertical mobility also transforms safety from a human challenge into a mathematical one. Traditional driving relies on human reaction times, which are slow and consistent and prone to error. In contrast, automated flight systems operate on timescales measured in milliseconds, constantly recalculating trajectories, monitoring airspace, and adjusting thrust. The physics of collision avoidance becomes a problem of probability and optimization rather than reflex. When vehicles communicate with one another and with the city itself, sky becomes a coordinated system rather than a chaotic free-for-all. Accidents, while never eliminated entirely, become statistically rare events rather than daily occurrences. In this sense, the physics of flight aligns naturally with automation, making aerial mobility potentially safer than ground transportation once the system matures. The psychological impact of vertical movement should not be underestimated. Humans evolved on flat terrain, and our intuition reflects that heritage. Yet history shows that intuition adapts quickly when technology reshapes experience. Elevators once seemed terrifying, and skyscrapers were viewed as unnatural intrusions into the skyline. Today they are mundane. Flying cars and vertical cities will follow the same trajectory, moving from novelty to necessity. As people adjust to a world where up and down are as familiar as left and right, physics does not change human nature, but it expands the environment in which human nature operates, offering new freedoms while demanding new responsibilities. At a deeper level, the physics enabling flying cars reflects a broader pattern in technological evolution, the miniaturization and decentralization of power. Just as computers shrank from room-sized machines to devices in our pockets, flight is shrinking from massive aircraft to personal vehicles. This trend is not accidental. It is driven by the exponential improvement of control systems, sensors, and materials, all governed by physical laws that reward precision and scalability. When forces can be measured accurately and controlled finely, systems no longer need to be large to be effective. Small becomes powerful, and personal mobility enters the realm once reserved for nations and corporations. The redesign of cities around vertical flight also has profound social consequences. When transportation becomes faster and more flexible, the rigid separation between residential, commercial, and industrial zones begins to blur. Physics enables this by reducing the cost of movement, making distance less relevant to daily life. People gain the freedom to live farther from traditional center without sacrificing access, potentially easing overcrowding and redistributing opportunity. Cities become less like rigid machines and more like dynamic organisms, constantly adjusting to patterns of movement and energy flow. In this sense, the physics of flying cars is inseparable from the physics of civilization itself, where flows of matter, energy, and information shape collective behavior. Ultimately, the question is not whether flying cars are physically possible, because the equations have already answered that. The real question is how gracefully we integrate them into the complex systems we call cities. Physics provides the foundation, but design, policy, and imagination determine the outcome. When technology aligns with physical law rather than fighting it, progress accelerates rapidly. Vertical takeoff, distributed propulsion, and intelligent control are not violations of nature. They are expressions of it, revealing possibilities that were always present but previously unreachable. As cities rise into the sky, they do so not in defiance of gravity, but in harmony with it, guided by equations that have been waiting patiently for us to catch up. As flight technology evolves, it no longer follows a single path but branches into multiple expressions of the same physical principles. One of the most promising directions emerges from magnetic levitation, a concept rooted in the fundamental forces of electromagnetism. When magnetic poles repel and unlike poles attract, stable suspension becomes possible with no physical contact at all. This absence of friction is not merely convenient, it is transformative. Friction is the silent tax on every machine, converting useful energy into waste heat. Remove it, and motion becomes smoother, faster, and vastly more efficient. While maglev has already proven itself on the ground through high-speed trains, its principles extend naturally into the air. When combined with precise electronic control, magnetic stabilization can reduce vibration, increase efficiency, and allow vehicles to hover or glide with extraordinary steadiness. The sky, once turbulent and unpredictable, becomes a controlled electromagnetic environment where Motion is guided as much by fields as by engines. Alongside maglev concepts, drones represent a crucial evolutionary step toward personal flight. Drones succeeded not because they defied physics, but because they embraced it honestly. Instead of relying on brute force, they used distributed lift, multiple rotors working together to maintain stability. Each rotor contributes a small amount of force, and collectively they achieve balance through constant adjustment. This architecture mirrors nature itself, where systems are robust not because they are simple, but because they are redundant. Birds, insects, and even schools of fish rely on distributed control to adapt instantly to changing conditions. In flying vehicles, this same principle allows machines to respond to wind gusts, obstacles, and sudden shifts in load with precision that would overwhelm a human pilot. The physics here is subtle but powerful. Stability emerges not from rigidity but from responsiveness. As drones scale up, their transformation into human-carrying vehicles is less dramatic than it appears. The equations governing lift do not change when mass increases. They simply demand more power and stronger materials. Advances in composite structures, carbon fiber, and graphene-based materials provide exactly that strength without excessive weight. The result is a class of vehicles that behave less like airplanes and more like dynamic systems, constantly negotiating with the air around them. In this context, flight becomes an ongoing conversation between machine and environment, mediated by sensors and algorithms that interpret the language of physics in real time. The vehicle does not force its way through the sky, it listens, adjusts, and flows. This evolution naturally leads to automation, not as a luxury but as a necessity. The sky cannot be safely shared by millions of flying vehicles guided solely by human judgment. Reaction times are too slow, perception too limited, and decision-making too inconsistent. Artificial intelligence, however, thrives in precisely these conditions. It excels at pattern recognition, prediction, and optimization skills that align perfectly with the demands of aerial navigation. By continuously analyzing trajectories, weather data, and nearby traffic, automated systems can anticipate conflicts before they arise. Physics, again, provides the framework. Motion follows predictable laws, and when those laws are encoded into algorithms, the future becomes calculable within narrow margins. Safety, once dependent on vigilance and luck, becomes a statistical property of the system. Automation also redefines what it means to control a vehicle. Instead of steering wheels and pedals, future pilots may interact with intent-based interfaces, specifying destinations rather than maneuvers. The underlying systems translate intent into motion, selecting paths that minimize energy use, noise, and risk. This abstraction mirrors the evolution of computing, where users no longer manipulate individual transistors, but work with layers of software built on physical principles they rarely see. The physics remains essential, but it recedes into the background, enabling complexity without overwhelming the human mind. In this way, flying vehicles become extensions of urban infrastructure rather than isolated machines, seamlessly integrated into the fabric of daily life. The implications for cities are profound. Once movement is no longer constrained to the ground, urban design undergoes a phased transition. Buildings cease to be endpoints and become intersections. Elevators extend beyond interior shafts and connect directly to aerial corridors. The boundary between architecture and transportation dissolves, replaced by hybrid structures that manage both space and flow. Physics dictates that vertical movement requires careful control of forces, airflow, and structural integrity, but modern engineering meets these demands with elegance. Smart materials adjust stiffness in response to load, surfaces channel wind rather than resist it, and embedded sensors monitor stress continuously. Cities begin to behave less like static monuments and more like living systems, responsive to the forces acting upon them. Automation further enhances this adaptability by allowing cities to self-regulate. Traffic patterns shift dynamically based on demand, weather, and energy availability. During peak hours, aerial corridors expand and contract like arteries, distributing flow efficiently. At night, energy usage drops and systems enter low power state. This responsiveness reflects a deeper physical principle. Systems that minimize energy dissipation tend to be stable. By aligning urban design with this principle, future cities achieve not only efficiency but resilience. Disruptions are absorbed rather than amplified, and the city maintains functionality even under stress. Noise, often cited as a barrier to aerial mobility, also yields to physics-informed design. Sound is a vibration transmitted through air, and by shaping airflow. Rotor geometry, engineers can dramatically reduce acoustic impact, lower rotational speeds, distributed propulsion, and active noise cancellation techniques transform what would have been a roar into a hum barely distinguishable from background sound. Physics does not forbid quiet flight, it simply demands careful management of energy transfer. When this is achieved, the sky becomes a shared space rather than an intrusion, and public acceptance follows naturally. The marriage of automation and flight also reshapes economic and social patterns. When transportation becomes faster and more predictable, time itself becomes a different resource. Commutes shrink, access expands, and opportunities redistribute. Physics underpins this transformation by reducing the cost of movement in both energy and attention. People no longer need to devote cognitive effort to navigation, freeing mental space for creativity and interaction. Cities become platforms for human activity rather than obstacles to it, their complexity managed by systems that operate quietly in the background. At a philosophical level, the rise of automated aerial mobility challenges long-held assumptions about control and trust. Humans have historically equated safety with direct oversight, believing that hands-on control is inherently superior. Yet physics and statistics tell a different story. Systems governed by precise measurement and rapid feedback outperform those guided by intuition alone. Trust shifts from individual skill to collective design, from heroism to reliability. This transition mirrors earlier technological shifts, such as the move from manual calculation to electronic computing, where initial skepticism gave way to dependence as performance proved undeniable. As these technologies mature, the sky becomes an extension of the city rather than a separate realm. Movement through air feels ordinary as movement through streets, guided by invisible architectures of data and force. The physics that once confined flight to specialists now enables it for everyone, not by simplifying nature, but by understanding it deeply. Automation does not replace human agency, it amplifies it, allowing individuals to operate within systems of complexity that would otherwise be unmanageable. In this sense, flying vehicles and automated navigation represent not just a technological upgrade, but a redefinition of how humanity interacts with the physical world, transforming constraints into pathways and turning the sky into a shared domain of possibility. Every great transformation in transportation has ultimately been an energy story. The horse gave way to the steam engine, steam to oil, and oil to electricity. Each transition unlocking new scales of motion and reshaping civilization. Flying cars and future cities follow this same trajectory, driven not by fantasy, but by the relentless improvement of how we generate, store, and distribute energy. Physics places strict limits on energy density, yet within those limits lies enormous room for innovation. Electric propulsion stands at the center of this shift, because it converts energy into motion with remarkable efficiency. Unlike combustion engines, which waste most of their energy as heat. Electric systems deliver power directly where it is needed. This efficiency is not merely economical, it is structural. When energy losses shrink, vehicles can be lighter, quieter, and more reliable, making flight compatible with dense urban environments. Battery technology often appears to be the bottleneck, but this perception overlooks the exponential nature of technological progress. Energy storage has steadily improved through advances in chemistry, nanostructures, and manufacturing techniques. Modern batteries are no longer passive containers of charge, they are active systems that monitor temperature, load, and degradation in real time. Physics governs the movement of ions and electrons within these systems, and by engineering material at the atomic level, scientists have learned to guide those movements with extraordinary precision. As a result, batteries become safer, faster to charge, and longer lasting, supporting flight cycles that would have been unthinkable just decades ago. Beyond batteries, hybrid systems incorporating supercapacitors and even hydrogen fuel cells extend range and flexibility, creating an energy ecosystem rather than a single solution. Energy generation itself is undergoing a parallel transformation. Future cities are not powered by distant, centralized plants alone, but by distributed sources woven into the urban fabric. Solar panels embedded in buildings, roads, and even vehicle surfaces convert ambient energy into usable power. Wind, often dismissed as incompatible with cities, becomes viable when harnessed at smaller scales through vertical axis turbines integrated into architecture. Physics teaches that energy flows naturally from high potential to low, and smart cities are designed to capture these flows wherever they appear. Waste heat from buildings powers nearby systems, breaking energy from descending vehicles, feeds back into the grid, and surplus generation is stored for peak demand. In this tightly coupled system, flying vehicles are not energy burdens but participants in a larger cycle of exchange. This energy integration fundamentally changes how cities are designed. Skyscrapers, once symbols of static ambition, evolve into dynamic transportation hubs. Their height, previously a challenge, becomes an advantage. Elevated platforms reduce the energy required for vertical ascent while gravity assists descent, allowing vehicles to recover energy through regenerative systems. Physics rewards this symmetry. Energy invested in climbing is partially reclaimed in falling, reducing net consumption. Buildings become nodes where energy, information, and movement converge. Elevators no longer stop at rooftops but extend outward into the sky, connecting directly with aerial corridors. The distinction between building and vehicle blurs, replaced by a continuum of motion and structure. These vertical hubs also address one of the most persistent challenges of urban life: congestion at ground level. When transportation shifts upward, streets are relieved of pressure, freeing space for pedestrians, green areas, and social interaction. Physics does not dictate that cities must be noisy, crowded, and polluted. Those are consequences of historical design choices. By redistributing movement into 3 dimensions, future cities align more closely with the natural efficiency of open space. Skyscrapers, acting as transfer points, organize this movement with mathematical precision, routing vehicles through layered pathways that minimize interference and maximize throughput. The city becomes a 3-dimensional circuit with energy and traffic flowing along optimized routes. The structural demands of these hubs push architecture into new territory buildings must accommodate. Dynamic loads from docking vehicles, shifting wind patterns, and variable energy flows. Advanced materials rise to meet this challenge, combining strength, flexibility, and intelligence. Smart alloys adjust shape under stress, composites distribute forces evenly, and embedded sensors provide continuous feedback. Physics again is the guide, ensuring that structures remain within safe limits while adapting to changing conditions. Rather than overbuilding for worst-case scenarios, designers rely on real-time data to maintain stability, reducing material use and environmental impact. The city becomes lighter, both physically and energetically. Energy management within these hubs is equally sophisticated. Skyscrapers function as microgrids, balancing supply and demand internally before interacting with the wider network. When vehicles arrive, they draw power not just from the grid, but from locally stored energy optimized for rapid transfer. When they depart, excess energy from braking or descent is absorbed and redistributed. This localized control enhances resilience, allowing parts of the city to operate independently during disruptions. Physics favors such modularity, as systems composed of semi-autonomous units tend to be more stable than monolithic ones. The result is a city that can bend without breaking, adapting to both routine fluctuations and unexpected events. The social implications of energy-integrated vertical hubs are profound. Access to transportation becomes more equitable when mobility is embedded into everyday structures rather than confined to specialized facilities. Homes, workplaces, and public spaces connect seamlessly to aerial networks, reducing dependence on centralized terminals. Time, once lost in transit, is reclaimed, altering daily rhythms and priorities. Physics underlies this transformation by reducing the energy cost of movement, making speed and accessibility features of the environment rather than privileges of wealth. Cities become more fluid, less constrained by geography, and more responsive to human needs. Environmental benefits emerge naturally from this alignment with physical principles. Electrified flight produces no local emissions, and when powered by renewable sources, its global footprint shrinks dramatically. Noise pollution, mitigated through careful aerodynamic design, recedes into the background. Green spaces expand as ground-level infrastructure is repurposed, improving air quality and thermal regulation. Physics teaches that systems in balance tend towards stability, and by harmonizing energy use, transportation, and architecture, future cities approach such balance. They become ecosystems rather than machines, sustained by continuous flows rather than constant extraction. At a deeper level, the fusion of energy systems and vertical architecture reflects a shift in how humanity relates to its environment. Instead of imposing rigid grids onto the landscape, cities evolve in dialogue with physical forces. Sunlight, wind, gravity, and motion are no longer obstacles to be overcome but resources to be cultivated. Flying vehicles and skyscraper hubs are expressions of this philosophy, embodying an understanding that progress accelerates when technology works with nature rather than against it. The equations governing energy and motion have always been there, patiently describing what is possible. As we learn to listen more closely to them, our cities rise not just higher, but smarter, more efficient, and more attuned to the universe that shaped them. The concept of a smart city is no longer science fiction, it is emerging as a physical reality, shaped by the interplay of sensors, computation, and artificial intelligence. These cities are not merely collections of buildings and streets, but dynamic systems capable of observing, learning, and adapting in real time. The physics of information underpins this transformation. Data, after all, is a form of energy transmitted, stored, and processed according to precise laws. Just as electricity flows through conductors and heat diffuses through materials, information moves through networks constrained by bandwidth, latency, and entropy. Understanding these constraints allows engineers to optimize urban systems, ensuring that energy, traffic, and resources are allocated efficiently and that disruptions are absorbed without cascading failure. In a smart city, flying vehicles and automated aerial corridors are integrated into a larger ecosystem of sensors and control systems. Each vehicle communicates continuously with others, with building hubs and with centralized computational nodes. This communication is not haphazard, it is governed by algorithms that predict trajectories, monitor energy use, and anticipate congestion before it occurs. Physics provides the rules of motion, while mathematics enables prediction and optimization. The result is a city that behaves almost like a living organism, responding dynamically to human activity and environmental conditions. Congestion that would paralyze conventional streets becomes a manageable wave, dissipating through adaptive routing and synchronized flow. The integration of AI into urban infrastructure also transforms energy management. Buildings, vehicles, and public spaces become active participants in a responsive energy network. Solar energy captured during the day can be stored and redirected to charging stations for aerial vehicles at night. Energy recovered from braking or descending vehicles can be fed back into the grid. The city becomes a complex feedback loop, continuously balancing supply and demand. Physics ensures that energy is conserved, but human ingenuity determines how it is allocated. This synergy allows cities to support high-density aerial mobility without overtaxing their resources, creating a sustainable system in which motion, energy, and information circulate harmoniously. Automation extends beyond logistics into maintenance and safety. Every moving vehicle and structural component is monitored in real time with predictive algorithms, detecting wear, stress, or environmental hazards long before they become problems. Sensors embedded in streets, rooftops, and air corridors transmit continuous streams of data, which AI interprets to coordinate repairs, reroute traffic, or adjust flight paths. The physics of forces and material limits becomes a language spoken fluently by machines, enabling cities to anticipate and prevent accidents rather than merely react to them. Safety is encoded into the very fabric of urban life, not imposed externally. Perhaps the most transformative aspect of smart cities is their adaptability. Traditional urban planning assumes static conditions, yet human activity and environmental factors are anything but constant. In a smart city, the allocation of aerial lanes, energy distribution, and traffic control are fluid, responding to real-time demand and predictive modeling. Physics again provides the constraints, defining how quickly vehicles can accelerate, how structures bear weight, and how energy flows. Within those boundaries, the city continuously reorganizes itself, optimizing efficiency, safety, and comfort. It is a system of perpetual adjustment, where every component communicates and coordinates with others to achieve collective stability. Flying cars and vertical mobility redefine human freedom within these smart systems. Distance, once a limiting factor in daily life, becomes negligible. Vertical corridors allow residents to move quickly between work, education, and leisure, liberating time for creativity, collaboration, and innovation. The physics of flight lift, thrust, Energy efficiency intersects with the mathematics of optimization to create a network in which motion is effortless and continuous. Urban life becomes layered, multidimensional, and deeply interconnected, yet it remains navigable because the system constantly mediates complexity on behalf of its inhabitants. This evolution also fosters resilience. Cities are increasingly vulnerable to natural disasters, climate change, and infrastructure failures. Smart systems, informed by real-time data and governed by predictive models, can respond to floods, storms, and earthquakes by rerouting traffic, adjusting energy flows, and deploying emergency resources instantly. The physics of these interventions, fluid dynamics for water, structural mechanics for building, and energy transfer for critical systems, is fully integrated into decision-making algorithms. In this way, the city becomes a self-correcting organism capable of maintaining function even under extreme stress, reducing risk and preserving life. Finally, the combination of flying vehicles and smart city infrastructure redefines civilization itself. Humans are no longer confined to two-dimensional grids, but can navigate a volumetric urban landscape. Physical laws still govern every movement, every energy transaction, and every structural interaction, yet the laws are harnessed and amplified through technology, enabling possibilities once relegated to imagination. Cities are not only functional spaces but platforms for human potential, expanding creativity, efficiency, and opportunity. Physics, mathematics, and computation converge to create an environment where humans and machines coexist seamlessly, where energy, information, and motion are optimized, and where the dream of flight becomes a routine part of everyday life. In this vision, technology does not simply support civilization, it transforms it, elevating humanity into a new dimension of possibility, freedom, and sustainable progress. As we gaze toward the cities of tomorrow, it becomes clear that the future is not just about flying cars or dazzling technology. It is about harmonizing physics, energy, and intelligence to create urban environments that are safer, more efficient, and more human-centered. Vertical mobility, smart infrastructure, and integrated energy systems will redefine how we live, work, and move, turning the sky above into a new frontier of possibility. The laws of physics remain our guide, but human ingenuity, imagination, and collaboration transform those laws into a world where freedom, sustainability, and innovation coexist seamlessly. Thank you for watching, for exploring these possibilities with curiosity, and for daring to imagine a future where cities rise, flight becomes ordinary, and humanity reaches new heights together. Your interest and engagement keep the vision alive.